So welcome back, friends. Okay, so we were looking at this beautiful mathematical marvel of equation which Dirac has constructed essentially. So he started again, just to recap, he started with the condition that E should be there should be a linear dispersion relation, which we have seen in couple of classes ago, essentially that there E should be the E operator, the energy operator should not be quadratic but should be linear, and it should be linear in momentum and mass essentially. And then to achieve that, he multiplied with some matrices which we call or operators, okay, and then he derived the conditions on these operators which we have seen, and we have found that these operators can exist and there are solutions for these operators which are nothing but alpha and beta matrices. After writing these solutions and then re-expressing them in terms of something called the gamma matrices, so the alpha and beta matrices just become gamma matrices. You can write it in a very nice covariant fashion, which is given by this particular beautiful equation, which is I del slash minus m is equal to 0, which is the Dirac equation for a free particle. We have not yet started looking at the solutions of this Dirac equation for a free particle essentially, but as of now we are trying to understand what is the structure of the wave function essentially. And what we have been seeing is that this matrix, though it looks like a scalar, its in actuality is a matrix equation, because this is a matrix essentially. So the left hand side I del slash minus m times psi is equal to 0, it is actually a matrix equation. Now because we can expand the left hand side like we did last time, I gamma 0 gamma mu del mu can be expanded in this particular fashion. So I del 0 I mean gamma 0 del 0 is nothing but beta, which has upper 2 by 2 matrices 1 2 by 2 and minus 1 for the lower 2 by 2, and the beta alpha I is nothing but sigma matrices with opposite signs in the off diagonal entry essentially. Substituting them back into this relation essentially into this particular form, we have written in this particular fashion essentially that it becomes a bunch of a 2 by 2 matrix made up of 2 by 2 matrices themselves. So it is in total a 4 by 4 matrix essentially. In total it's a 4 by 4 matrix, and this 4 by 4 matrix should have a wave function of this particular type, which should be 4 by 1, such that you can get a scalar psi is equal to I del slash psi is equal to 0 on the right hand side essentially. Okay, so what we have seen is this psi is a 4 component wave function essentially. It's a 4 component wave function which is in a vector space spanned by the gamma matrices. We will come to the more mathematical properties of these gamma matrices a bit later on, and the spaces which it spans, but for the present let us know that such a vector or a psi is no longer a scalar. Okay, the important point here is that the wave function is no longer a scalar, but such a vector is called a spinor. Okay, it is called a spinor because a vector is a wave function which is in a it's a vector in a vector space spanned by the gamma matrices. So it's a vector space spanned by the gamma matrices. So it is a different kind of a wave function, and this wave function is called a spinor. As we will see later on that this is an extremely important point in the understanding of the Dirac equation, because the Lorentz indices are different and the gamma indices are different. The spinorial indices are different essentially. The spinorial indices go with the gamma matrices essentially. The gamma matrix index, each gamma matrix has an index I and j essentially because it's a matrix. And the spinorial indices will go with that, whereas the the Lorentz indices are essentially the vectorial indices. So this confusion should not be there for any student, and that's the reason why I am insisting this again and again essentially. So let's further understand this particular thing, this particular operator in much more detail. Now let me expand even the 2 by 2 on the top essentially. So let me expand. So let me call this equation as equation 1, equation say 1 for this particular class essentially, and then further proceed to understand how does it look like essentially. So the gamma 0 we have seen essentially, we have it is 1 0 0 minus 1. So what we have to expand essentially is only the off diagonal entry essentially. So if we expand the entire full off diagonal entry, the full form of the 4 by 4 form of the Dirac equation, again I am repeating, it is a matrix equation, okay, will be I del 0 minus m 0 0 I del 0 minus m. So this is the unit matrix, I am expanding it, which multiplies I del 0 minus m essentially of this particular from equation 1. And the thing with del x minus I del y del x plus I del y del z minus del z. The upper 2 by 2 matrix is essentially given by the sigma matrices essentially. So the sigma matrices multiplied by I del, okay. So this has a form which is given in this particular fashion essentially, okay. Now the lower 2 by 2 block is minus I del z minus del x plus I del y minus del x minus I del y del z, and this part would be I del 0 minus m 0 0 minus I del 0 minus m. So the full wave function is can be written in terms of psi 1, psi 2, psi 3, psi 4. So the Dirac equation is essentially each equation multiplying this psi 1, psi 2, psi 3, psi 4 is equal to 0 essentially. It's a matrix equation. This is a 4 by component wave function essentially. And this entire thing we write it in a simpler fashion in terms of I del slash minus m and to psi is equal to 0. If we expand this, this entire thing becomes in this fashion. Now you can now what we have seen earlier in the class essentially, that in the earlier classes is that if I iterate this equation alpha times p plus beta times m and square it, okay, and square it, okay, if you multiply it again, it should give me back, the condition is that it should give me back e square is equal to p square plus m square essentially, okay. We have seen that that was the starting point essentially. So we have seen that if I start with this e is equal to alpha times p plus beta times m and I square it, the alpha matrices and the beta matrices act in such a way that e square should be equivalent to p square plus m square. So it turns out exactly for that reason, okay, if you iterate the Dirac equation, so if you start by multiplying the Dirac equation on the top of it again essentially, so if you multiply I del slash plus m, I del slash minus m into psi, so each component, okay, so you expand this entire thing and you will end up having Klein-Gordon equation for psi 1, psi 2, psi 3, psi 4. So if you keep iterating it essentially, you will end up having the Klein-Gordon equation. So, for the first solutions, the first insight of the Dirac equation, what we have is that the solution which is psi 1, psi 2, psi 3, psi 4, each of the components of the Dirac spinor satisfy the Klein-Gordon equation. Each of these components of this Klein-Gordon, okay, each part of the solution satisfies the Klein-Gordon equation. So, this is nothing this spine I told you that this special vectors are called spinors, okay. And these spinors are essentially satisfy each of the spinors, components of the spinors satisfy the Klein-Gordon equation. So, the Klein-Gordon equation is not going anywhere. In fact, as we will see later on, essentially that the Klein-Gordon equation itself can be written in terms of a two component format essentially, and then it can be useful for deriving meaning non-relativistic reduction. As I think I mentioned in the class somewhere that there are other ways of deriving the non-relativistic reduction. Essentially, another form of doing the same thing would be is actually to use the two component form for the Klein-Gordon equation essentially. That is for especially for the charged scalar field equation. Okay, so now okay, this is the most important thing that to remember that the solutions of the Dirac equation are called the Dirac spinors. Okay, the solutions of the Dirac equation of the Dirac spinors, and each of them satisfy, okay, each of them satisfy the Klein-Gordon equation. Now, the question is which of them satisfy positive energy and which of them satisfy the negative energy. That is the question essentially. To do that, okay, each of them satisfy the positive energy solutions or the Klein-Gordon equation solution. So, each of them is a solution to the Dirac spinor. So, the Dirac equation called Dirac spinors, spinors of vectors spanned by, okay, which are vectors which are spanned in the gamma matrices vector space essentially, and and whose components satisfy the Klein-Gordon equation. Now, you can see that going to the rest frame, okay, now let us go to the rest frame of the particle, okay, the solutions can be represented in terms of, okay, rest frame solutions. Solutions of the Dirac equation. So, what are the solutions of the Dirac equation? So, the solutions of the Dirac equation are just going to the rest frame essentially. Again we just set essentially p bar is very small essentially. So, this is going psi alpha the particle is at rest frame in its own frame, essentially I alpha S frame of the particle epsilon I m of t times some psi alpha of 0, psi alpha of 0. Okay, these are the solutions. So the particles always come in terms of these components essentially. Now alpha is equal to plus 1 for alpha is equal to 1 and 2, and minus 1 when alpha is equal to 3 and 4. So the first two components of psi 0 in the rest frame have a minus sign, they have a plus sign, so that they corresponds to positive energy solutions, and the next two solutions which are essentially minus sign, which corresponds to negative energy solutions essentially. So psi 0 1 0 0 0, psi 1 psi 1 one second, let us get this notation right. It is psi 1 of 0, psi 2 of 0 is equal to 0 1 0 0, psi 3 of 0 is equal to 0 0 0 1 0, psi 4 of 0 is equal to 0 0 0 1. Okay. So now that I have set the notation, let me just explain this again a little bit more. The solutions of the Dirac equation, I take the static limit, essentially I take the limit in which all the off diagonal part goes to 0. That means the p bar is equal to 0. So these are solutions which are static, or in the rest frame of the particle. The particle is not moving, it is sitting there essentially, which has only the mass essentially. So you can solve these solutions, the equations very simply, because the off diagonal entries are not there. Okay, and in that case, but still the components are there essentially. You have these components essentially. These components will correspond to so there will be four classes of these components. So each of these components will have a rest frame solution which is called psi 0. So each of this psi 0 is essentially given in this particular fashion, where psi 1 of 0 is equal to 1, where the first component is 1 and all the rest of the components are 0. Psi 2 of 0 is means psi 2 will become active and all the rest of the contents becomes 0. Psi 3 of 0 is first 2 and the last one becomes 0 and the third one becomes active, it becomes 1, and psi 4 is essentially for the 4. Now why do you distinguish between each of these components in this particular fashion is because the first two end up having positive energy solutions, because they can be given in this particular fashion purely because of the sign of the derivative term in the t. Okay, you can see that there is I del t here, essentially I del 0 is nothing but I del t, whereas the next two solutions will have negative energy solutions, which is obvious from this equation essentially. Okay, you set the off diagonal entries to 0 and then you see the static solutions very simply, that the first two energies will have positive energy solutions and the next two things will have negative energy solutions, just from noticing from this equation. Okay. Now these components would be psi up and down. So these are called spinors essentially. These are these four spinors essentially which you have. It is a 4 component spinor. This is called a Dirac spinor. Now the question is, first thing we notice is a disappointment in some sense, in then that we cannot escape negative energy solutions. So, even after building this entire thing, okay, okay, you see that in the Dirac equation you cannot escape negative energy solutions essentially. Okay. So, the entire construct of the Dirac equation was trying to say that okay, maybe if you do not take the square root, maybe if you do not take the square of the energy operator, but if you take the linearity of the negative energy operator, you will end up having only the positive energy states, okay. But it does not happen in that sense essentially that uh, that that does not work out, because in the end of the day, as we have seen, Klein-Gordon equation still exists essentially, because the way we constructed the norm essentially, the energy operator in terms of alpha and beta matrices, they may hide the point that uh, the Dirac operator, meaning that the negative energies, that the energy is always positive, but in the end of the day they had to satisfy E square is equal to P square plus M square, because the alphas and betas are constructed with those conditions, and that is precisely the reason why psi 1, psi 2, psi 3, psi 4 satisfy the Klein-Gordon equation essentially. That is the reason why they satisfy the Klein-Gordon equation. And the way, because of that construction of the conditions on the alpha and beta matrices, the inherent property of relativity that it will always predicts negative energy solutions is not lost in the Dirac equation, as you have seen in the 4 component form, in the full 4 by 4 form essentially. Because if you look at just the solutions which are at the rest essentially, when the particle has 0 momenta, you see that you cannot escape negative energy solutions. So, you will have the first 2 components which are positive energy, the next 2 parts are negative energy. There is no way of escaping negative energy solutions. Now, you can ask the question that why, but oh, then this is just Klein-Gordon equation in different form or some such thing essentially. But there is a difference between, the main difference between Dirac equation and the Klein-Gordon equation is that not in, because of the presence of negative energy solution, that is not the main difference is that Dirac equation, Dirac solutions have a positive norm. So, Dirac solutions you can see that, as we will see essentially, that they have a positive norm essentially. So, and for that I need to introduce another operator essentially, we will see a bit later, that they have a positive norm. So, whereas such a positive norm is not possible in Klein-Gordon equation. So, this distinguishes the Dirac equation from the Klein-Gordon equation. So, even with positive norm, so what Dirac equation tells you that is even with a positive norm, okay, they have a positive norm, you can derive the continuity equation and so on. So, essentially, okay, the even with a rho, with a probability current density with a rho with a positive norm, one cannot escape. negative energy solutions. So, you can define the rho or the rho mu essentially, okay, rho the probability density in Dirac equation solutions, but cannot escape, we will come to that point, essentially cannot escape negative energy solutions. So, this is the main takeaway of the Dirac equation. Now, we will see more solutions in the coming lecture. Essentially we will see more solutions and expressions of them essentially. So, this is the main takeaway. The main takeaway is that okay, Dirac equations can have positive norm. So, you can calculate the norm from the this thing, but you cannot escape the negative energy states, you can never escape. So, they seem to be much more fundamental in relativistic quantum mechanics, that negative energy solutions always exist in relativistic quantum mechanics essentially. Okay, I will stop here. Okay, thank you very much, and I will see you in your next lecture.